Hello, my name is Eyyu Sari, and I'm here to present differentiable masks for pruning convolutional and recurrent networks. Let's start by the introduction. We know that deep learning has achieved very good performance over a lot of different areas, such as computer vision and natural language processing. However, to do so, the model had to get bigger and bigger. Currently, there is a need for putting AI on the edge. For instance, if we want to put some neural networks on an autonomous car, we need to respect some constraints of real-time computation, for instance. Also, if we want to put some AI on the mobile devices, we would like to keep the privacy of the users. Therefore, we don't want to upload some data to the cloud. To do so, we will need to have a model that is able to respect real-time and model size constraints. However, the current size and the current types of model don't fit at all. We can see that it ranges from up to several hundreds of megabytes to even sometimes gigabytes. Therefore, we need to do something about it. That's why the research community has developed a set of tools called neural networks compression methods that are able to deal with this issue. One of them is pruning. Pruning basically removes parameters inside the network. We say that the pruning is structured if the way the parameters are removed make it possible to gain some speed up at inference. For instance, if we will happen to remove all the weights related to filters, then we won't have to compute it anymore, and we will gain some speed up. One of the methods we took inspiration from this work is network slimming. It's a very simple and elegant method that applies L1 regularization on the Batchelor parameter inside the convolutional neural networks. After the training, we threshold the gamma parameters that are below a certain value. Therefore, it allows to prune the corresponding filters. While pruning is interesting, it's very tedious in practice to apply it. One of the main reasons is that the pruning happens after the network has been trained. And obviously, it was not meant to be pruned. Therefore, a huge gap happens, and we need to do a lot of rounds of fine-tuning to reduce the accuracy gap. Sometimes we are not even able to do so. Also, the methods that are developed are mainly developed for one kind of entity. For instance, a method that has been developed on weight pruning will be hardly applicable for filter pruning or subnetwork pruning, for instance. Finally, pruning is by definition equivalent to a hard thresholding and is therefore non-differentiable. In this section, I will present differentiable mask pruning that aims to deal with this issue. So DMP is a novel pruning algorithm that tries to tackle such issues. Mainly, we make the model prune during training. What does it mean? It means that while the model is training, within the epochs, some of the entity will get pruned by the way of the mask function. It allows for gradual pruning, therefore the model can recover and adapt for the entity being pruned. And also at the end, the model is basically already pruned, therefore no fine-tuning round is required, which helps a lot when we have to do a lot of iteration between different models. We don't want to lose time to fine-tune a model several rounds. It's a differentiable method, so the pruning is embedded inside backpropagation. It can be applied to any kind of entity, such as weights, filter, or nodes, or even subnetworks. Therefore, it's architecture agnostic because we don't require the apparition of batch norm layer, for instance, inside the network. We can use it for any kind of architecture, any kind of task, such as computer vision, natural language processing, speech, or multimodal learning, which was one of the main motivations of this work. So I'm going here to describe how the training is modified. So given a prunable entity X, we modify the training by adding a scaling factor alpha of dimension D. The dimension D will set the kind of pruning we want to do on our network. For instance, if alpha is a scalar, it is equivalent to sharing this value with all the subnetworks. Therefore, the subnetwork is pruned. If it's a filter, it's similar to doing filter pruning on a convolution. We also add a mask function that will return 1 if the value of the scaling factor is above a given threshold, or 0 otherwise. If it returns 0, it means that the entity is pruned. Inside the network, we replace the apparition of X by I alpha times I of alpha times X, so that when alpha is below the threshold, the entity will be pruned. We push alpha towards 0 by the mean of a L1 regularization term that we add to the loss function. So as I mentioned earlier, pruning is equivalent to hard thresholding. Therefore, we cannot really use it inside the common scheme of backpropagation. We use a smooth approximation to counteract this fact. What I mean by that is that during the forward propagation, we are going to really use the hard thresholding function, the mask function, so that during the forward propagation, the values are going to be pruned. Indeed, the values will be 0. However, during the back propagation, we replace its derivative by the derivative of a smooth function that approximates it. Going here to describe how we can plug in the mask function. So you can see at the left that we have a ResNet side block, which is composed of 2 sets of convolution. In the middle, if we wanted to apply filter pruning, we will add a mask after each of those convolutions. However, if we wanted to remove the whole blocks, we will add a subnetwork mask, which is equivalent to a single number shared across the whole block. In terms of results, we can see that the method works well on ResNet 56 and Cypher 10. We can see that we are able to prune 12 out of 27 blocks, equivalent to a pruning ratio of 45.6%, with only a 1.2% increase in the test error. To show the versatility of our technique, we also apply it on a language multitask on the PTV dataset using a single LSTM cell. We can see that we are able to compress it by 18% while only increasing the test perplicity of 1 point, which is quite good because the 1-layer LSTM is underfitting in the Pentribunk dataset, but we are able to keep the accuracy close to the original one. So as a conclusion, I will say that DMP is a novel pruning method which aims to allow pruning while training. Therefore, we are able to do gradual pruning so that the network can adapt. Otherwise, if all the prunable entities are pruned at once, like in the other methods, then we have to do a lot of fine-tuning to recover the accuracy, which is not needed in our case. We can also prune any entity. The method is generic. It can be applied to the subnetworks, the filter, the weights, and so on. It's task and architecture agnostic. We can apply it for any kind of network, but also computer vision, natural language processing, speech, multimodal learning, and etc. So thank you very much for listening to the presentation. Take care.